All right, friends, I'm going to try to answer as many of these questions as I can. I haven't given them much thought, so this is mostly just off the top of my head. But we'll see where we go. So since binary operations are functions, is their injectivity or surjectivity ever discussed? I was wondering this because of the definition I saw that binary operations are functions, which got me curious about if they connect to subjects we've covered in previous courses. Yes, absolutely. We will talk about injectivity and surjectivity in case we've forgotten. Let's see. F from A to B is injective, or sometimes we call that one-to-one or one-to-one if each B in the if for each B in F of B. All right, so here's some, we're laying on some notation. This is the range of F, which is different than, which can be different from the codomain. Right, so the range is the set of all of the outputs. Sometimes we also call this the image of F. Okay, now the range or the image of F is a subset of the codomain, and sometimes it's equal to the codomain, but not always. But anyway, a function is injective if for each B and B there exists exactly one A and A such that F of A equals B. Essentially, you don't map to anything in B with two different elements. So for example, F of X equals X squared is not one-to-one, since F of 1 equals F of negative 1, and 1 does not equal negative 1. And then surjective, F is surjective if for each B in B there exists at least one A and A such that F of A equals B. So now this surjective is saying something about the codomain. So essentially, right here, notice this difference. B is in the image, and here B is any element of the codomain. So it's surjective if we can map to any element in the codomain with at least one, not exactly one, but at least one element. So yeah, binary operations are functions. We will actually use, we can think about some of the group structures using injectivity and surjectivities. We will think about, because there are these things called group actions. Don't want to talk about that. Let me say short answer, yes, right? Thinking about the fact that you're thinking about injectivity and surjectivity as soon as we mention a function is a good thing. Will we use it explicitly when talking about groups? I'm thinking ahead to some of the homework. I think there is at least one homework problem where thinking like this is a good idea. But yeah, knowing injective and surjective is a great thing to know. Well, it's a good reference for good proofwriting strategies. I know that's what this class is built off of, so that's why I asked. I would say I don't have a great answer. Maybe I should look into that. But Math 225 notes, I think, is a great a great resource. I think I don't know who taught it for whoever wrote this question, but Dr. Kim did a great job of like flow charting proofs for your scratch work, and I think that strategy is a really good one. I think it can be really effective. So a flowchart proof is like, maybe let's take an example from the homework. Oh, what do we, homework? What's an example that's not on the homework? Here, maybe let's prove that if star is a binary operation on set S with A, B, C, and S, then if A equals B, we have A star C equals B star C. A equals B, we have C star A equals C star B. All right, so what would a flowchart proof look like? So we would start with like, what are our assumptions? So let's prove one, and let's do our scratch work. We're going to assume star is a binary operation. This is essentially the first sentence. Binary operation on set S, and A, B, C are in S. Great. There's our statement. Now, what facts can we draw from that statement? Well, that means that, so star is a binary operation on set S. So that means star goes from S cross S to S. What else do we know? We know star of AB it can be written as A star B. That's the notation. Star of, right now I'm just writing down as many facts as I can that may or may not be useful that I can draw from the fact that star is a binary operation on S. I think, right, with that connecting to that previous question, star is a function. Okay, so that's all the stuff there. I guess A, B, C are in S, so A, B, C are elements of S. So I guess that means that star A, B, star A, C, star B, C, etc. are, we'll say, defined. Right, so because all those elements are in S, we're allowed to like plug them into our binary function. Here we have, right, star is a function. So maybe, right, I don't know exactly how Dr. Kim does this, but this is, my version of a flowchart. So star is a function. What does that mean? So what's the definition of function? Every input corresponds to, so star is a function. Every input corresponds to exactly one output. So, right, then in other words, just say that as if A equals B, then f of A equals f of B. That's saying the same thing, but using math speak. Okay, I think that's probably it there. Something else we can get. Let's see. Oh, since we have like S cross S, so if I'm going to use different variables. If X, Y, Z are in S, X, Y, W, X, Y, Z. This is just some facts about S cross S that I'm thinking of. If W, X, Y, Z are in S, then we say Wx equals yz if w equals y and x equals z. All right, so this is just like unpacking the first sentence. So now we have access to all these facts. And now, all right, we're going to also, if we're proving one, we're going to like further, this is maybe the second sentence, further assume, or maybe this goes in the first sentence too, assume A equals B. Okay. Now here's where you have to get creative and kind of take this all in. Like our goal, where's our goal? Goal is, what is our goal? We probably need more room, but A star C equals B star C. Okay, well, how can we get that? Right, let's like back up. Therefore, right, all right. Therefore, A star C equals B star C. Well, how could we get that? Well, that's just the definition. That's star AC equals star BC. That's literally the same thing using our definition up here. Or using this box up here. Okay, well, how do we get this? Right? Well, we can get that, right? This is true. So see, we're kind of like working backwards now, right? Because we're kind of stuck. We're kind of stuck up here, right? We know A equals B. We need to get here. We know all these facts. Well, okay, how do we get those things to connect? So now, all right, well, how could we get here? Well, now here we can use, right? We can get that from AC equals BC, right? So the fact that, so this fact here allows us to go from this statement to this statement. Okay, AC equals BC. Well, how do we, right? How could we get there from this? Well, if A equals B, okay, so this implies that where is it? Yeah, it's this definition here. Oh yeah, no, we got it. We got it, friends. We can move there from that definition. So now this is essentially this is our proof all laid out, right? We start up here, and then this gives us all these facts. And then we say, okay, so this is our base set of assumptions. And then we're also going to assume this, and we need to get here. So we move like that. So now this is the scratch work for your proof, and now you just need to formalize it. So Again, I don't know if this is exactly how Dr. Kim does it. We've just had lots of conversations about it, and I think it's a valuable strategy to try. And I would refer to your Math 225 notes. And we're gonna do a lot more proofs as well. We didn't do many that first week because there's just there's a lot of definitions and stuff we're digging into, but we'll be doing more proofs in class, and you'll learn how with experience and with feedback and things like that. You're probably gonna do things. Your proofs, all of you, your proofs are probably not going to be good in the beginning of the semester. That's fine. They will get better though. All right. Well, I've learned the precise definition of group and abelian group. I'm curious now what makes an abelian group so interesting. Study/research. Based on my very loose understanding of the definition so far, the only real difference is that abelian groups have a property that requires binary operation to be commutative. Yes, that is literally the only difference. Yep, that's the only difference. This one axiom switches properties of a group that much to cause certain things to be different from regular groups. Yes. Yeah, so commutativity is literally changes everything. Right? So like if you think about like solve ax equals b and solve xa equals b. So this is just a standard linear equation. Let's assume that we're, star is a binary operation. We're in some, let's set it up. Let G be a group, and then A and B are in G. So now, if the group is abelian, then we know that the solutions for these two different equations are exactly the same. And that's nice. And if we're not abelian, then we don't know that the solutions are the same. And that's, not as nice. Not as nice. It literally changes, everything. So that is, and they're both interesting. So abelian groups are interesting and non-abelian groups are interesting as well. A lot of people study non-abelian groups, non-commutative groups. It's called non-commutative algebra. And the reason why non-commutative algebra is so important is because linear algebra is non-commutative algebra. And linear algebra is super important. But there's also lots of algebra that's commutative that's also super important. So yeah, they're both very interesting, very fascinating, and very different beasts. All right. Will notes for this class be released on the week that we will use, or will they be released in advance of that? My goal, right, I'm kind of reworking all of the notes and expanding everything, and the goal is to have all the notes for the week out by Monday of that week. If you want to work farther ahead than that, then you can always read the textbook until we get to rings, and then we're just going to be relying on my notes. So, but I might be basing those off of a different textbook. So I will let you know. All right, in section 6 for questions for something. What is it really asking? Okay, so what is it saying? It's saying Z6. Understand the wording. Okay. Main question: how do we know the inverse of 5? Okay. Okay. All right. So awesome. Great question. This is very confusing. So let's do. So let's say, what is the inverse of 5 in Z6 star 6? And then let's do several. What is the inverse of 5 in Z6 plus 6? And what is the inverse of 5 in, let's do like Z8 times 8. That's going to be hard. Okay, so the first question is, what's the definition of an inverse? So that, if we don't know the definition of an inverse, then answering this problem is impossible. So we say that E in S is, and then we need to know what an okay, so this problem is hard because we need two definitions, at least two. Okay, we say E and S is the identity element with respect to binary operation star if A star E equals E star A equals A for all A in S. We say blank in S is the inverse of A in S if A star overline A equals A overline A equals E. Okay. Those are, so we need to know, first of all, what the identity element is. And then once we know what the identity element is, then we can attempt to find the inverse. So, all right. What is the inverse of 5 in Z6 with this weird multiplication? To first think about the inverse, we need to find the identity. And the identity in this situation, so identity element is 1, since 1 times A equals A, special multiplication times 1 equals A for all A in Z6. Right, so remember Z6 is 0, 1, 2, 3, 4, 5. Okay, so first of all, so now this is a question, what is the inverse of 5 in Z6 multiplication? So another way of writing this is 5 times x equals 1. Right, if we can solve this equation, then whatever we figure out, right, whatever we figure out for x, that's going to be the inverse of 5. Okay, and if we look at our multiplication table, we will see that 5 oops, that's the special multiplication. 5 times 5 equals 24. Sorry, 5 times 5 equals 25. And then if you mod out by 6, right, you get 4 times 6 is 24. So 25 divided by 6 is 4, remainder 1. So now we can write that the inverse of 5 in this special situation is 5. Or we also use that notation for the inverse. All right. What is the inverse of 5 in this other situation? Well, we need to figure out, well, what's the identity? So identity is 0 since 0 plus a plus 6 equals a plus 0 equals a for all a in Z6. Okay, so now this question is asking 5 plus what equals 0. So the equation we're solving here is different because there's a different identity. Right, if you look at the previous one, right, the equation we're solving there is 5 times x equals 1. Here it's 5 plus x equals 0. And we think about it a little bit and we see that if you add 1, 5 plus 1 is going to give you 0 in the special addition. So that means the inverse of 5 is 1, or since this is addition, sometimes we use the notation -5 equals 1. And all this is saying is the inverse of 5 here is 1. All right, and then I don't think we worked through a problem like this. So what is the inverse of 5 in Z8? Okay, so again, identity is 1. Identity is 1. So in real time, I don't even know if the identity exists. It should. 5 times the what is going to give us 1. So I'm just going to do, 5, 10, nope, 15, nope, 20, nope, 25, 25, yeah. Wait, is that right? Oh, 5. Oh, that's interesting. 5 is its own inverse again, I think. Hold on. So 5 times 5 equals, that's going to be 25. And then modulo 8. Yeah. So it's 3 remainder 1. Okay, awesome. So this, in this case, the inverse of 5 is also 5. Let's try one more. That's a coincidence, friends. 5 is not always its own inverse. What's the inverse of 3? 3, 6. The inverse of 3 is 3. It's a coincidence, I promise. All right, let's do the inverse of 7. Oh, God. 7 again? What? Maybe it's not a coincidence, and I don't understand what's going on. Oh. Okay. All right. You all should think about that. That's interesting. That's interesting. All right. Hopefully that helps. All right. Is closure under the binary operation always necessary to create a group? Yes. Yeah. Yeah, exactly. You're right. Right? Otherwise, it's not a binary operation. Yep. We always need closure. If you're jumping outside of the group, then it's hard to say much about the group structure, about the structure of the thing. So yeah, closure is super important. All right, is this the last one? Yeah. All right, after doing the first quiz, 2 issues. First issue, tend to panic. Okay. Yep, that's pretty common. Yeah, there is. Yeah, more preparation could help, but I always, yeah. So, I have lots of things to say. First of all, this is totally normal. Second, it might not be more preparation, it might be better preparation, right? So, more is not necessarily good, right? Because if you're doing more of like bad preparation, then yeah. like, so for example, let's say you're training to do a marathon, and you're just doing 100-meter sprints for your training. You're just doing as many 100-meter sprints a day as you can. Well, like that's, it's not going to be very helpful. So, what could more preparation be? I mean, the best. There's this thing. Oh, what's it called? It's called. If you look it up, there's a bunch of research about it. It's called successive relearning. So essentially, it's for definitions. This is like really powerful, and it can be powerful in other situations too. But essentially, it's essentially using flashcards effectively. It's like the research way to use flashcards most effectively, right? Flashcards aren't effective in all situations, but definition quizzes definitely effective. So flashcards for this class should be a tool that you use. And what you do is you do initial learning. So that means you have all of your definitions on flashcards, and you look at the flashcard, and you write down the definition, and then you look at the back, and if you get the definition 100% right, then you take that card and you set it off to the side. And if you get that definition wrong, it goes back in the back of the pile. Okay, so you go through this initial learning set where you get every single definition correct, right? And then you wait 12 to 24 hours. Well, I mean, it really depends. Let's say wait, at least, I don't remember the exact number, how long you should wait before another set, but I think it's at least 12 hours. I'd have to look into it. But essentially, you're waiting waiting long enough to forget. Long enough to forget. Because when you're doing these flashcards, right, you want to be relearning, right? So you want enough time to pass where the definitions aren't in your short-term memory, right? You want long enough time where the definitions move to your long-term memory. Because once stuff is in your long-term memory, it's like hard to get out, and that's where the learning happens, is trying to get it out. And then, wait at least 12 hours, and then, essentially you're repeating one. Get them all correct. Work through your pile, get every single one correct. If you get it wrong, put it in the back of the list. If you get it right, set it off to the side. And then you do that as many times, There's what does the graph looks like? Right, here's the graph. This is like number of repeats. So after the initial learning, right, if you don't do anything, right, I don't remember these exact numbers, but this is essentially what the graph looks like. It's increasing. So if you do one initial, right, one extra, like a lot of learning happens here. And then, okay, what is this? This is your grade. And then more learning happens if you do it twice. Essentially, right, this is called like the durability of learning. So, right, the more times you repeat it, the more durable the learning is, like the longer it lasts. And there's long-term studies about that too. Anyway, this graph is to show that there are diminishing returns. I'd have to look up the exact research paper, but I think like 0 to 1 is like a huge return. 1 to 2 is a pretty big return. 2 to 3, it's a return. 3 to 4, it starts becoming like probably not worth your time. So that's one thing you can do. Successive, like that's like literally like some of the best scientifically based ways to learn definitions and vocabulary in particular. Okay, so I hear we're panicking. All right, so how do we, maybe this successive relearning, you do all this successive relearning, but you still panic, and then you forget everything. Because what happens is, in your brain, this is your brain, you got long-term memory. That's huge. And then this is like short-term. And what makes us, what separates humans from many other animals is our long-term memory is amazing. Our short-term memory is like good, but not like really good. It's not like great. And right, there's a lot of, right, in order to like do well on a quiz or an exam or whatever, you need to take information from your long-term memory and get it to your short-term memory, and then from your short-term memory it goes down onto the paper. Now, if you start panicking, then what happens is emotions get in the way, right? They take up space, and they start blocking your neural pathways. Well, they're not like blocking your neural pathways, but your short-term memory is being used up to help deal with the anxiety or the stress or whatever else is going on. So it's not, I shouldn't say that your emotions are blocking that. Your emotions are kind of like taking up your short-term memory. Which means that you can't access your long-term memory, which is where all the stuff is. So how do we get out of this panic state? Well, first thing to do, is if it's really bad, you gotta see a therapist. No shame in that. I see a therapist. So if it's really bad, like I said, I might not be able to deal with it. Or my advice here is probably not going to help if it's really bad. If it's not so bad, here are some research tested things that you can try. One is, it's literally like it's super effective. 5-minute free write about why you are anxious. Right before you take the quiz, right before you take the quiz. That's super helpful. The research shows like it improves scores by 10%, up to 10% on average. So very effective. Just writing about your anxiety, writing about the quiz, like how you feeling. Because essentially, now they don't know exactly what's going on, but the theory is if you write about it before you take the quiz or the exam, you're essentially like getting a jump on those emotions, right? That emotional reaction that you have when you get into the quiz or whatever, and you deal with that and kind of get that out of the way before you have to use your short-term memory to access your long-term memory. So that's the rough idea there. Tips for over talks are where I immediately start feeling completely. Yeah, this one is also right. I used to struggle with all this stuff. That's why I know about it. I would end up feeling like this. This is actually why I have students write about this, is because I struggled with it a lot. And I thought, I was the only one. And then I found somebody that was writing a lot about it. I was like, oh, maybe this isn't as I'm not as unique in this as I thought. And then I started having my students write about it. And it's like, oh, this is like very common. So I think writing about it is good. That will help. Looking at those antidotes and trying to implement some of those antidotes, that's super helpful. When you notice it happening, right? Identify, right? What are the steps? The therapy steps is, all right, you notice that it's happening. The first thing you need to do is like name it. Be like, oh, this shit's happening right now. Okay, so just name it. That's the first step, is be able to identify it really quickly. Okay, this is happening. Cool. And then the next step, so maybe naming it will take, I don't know, weeks, days, months, whatever. And then you got to start constructing a counter narrative. Okay, now I'm really good at recognizing it. Now, what do I say to myself? What do I do? What counter narrative do I produce when it starts cropping up? What's going to be useful for me? And that's very personal, what's going to work for you. But maybe some of those antidotes could help from the toxic perfectionism antidote handout that I gave you. So, and then again, if it's real bad, then go to therapy. All right, friends, these were great questions. Did I answer everyone's questions? 3, 4. Yeah, okay, cool. I got to have all of them. I don't know if I'm always going to do all of them, but this week I was able to. So keep on keeping on.